Forecasting Part 2. So Part 1, recap. Learned about the basics of forecasting and talked about some qualitative methods for doing a forecast. Now we move into the numbers. We do some quantitative methods for forecasting. Both have their place. I'm a quant person, but totally understand. Been in a lot of situations where the qualitative forecast was the superior choice. And that situation by situation. And even when we do these quantitative forecasts, we do not suspend judgment. Judgment is still important here. And we still got to use our brain. Thank goodness, because it's brain usage that we get paid for. Grunt calculations, any monkey can do that. Put them in context. State whether they make sense or they don't make sense. Those are the people that make good money. They're the ones that do that. Okay. So we'll do some quantitative. So time series. Now there's a little bit of notation, and in the education speak, they say if you put a subscript on anything, business students start to cry. I think that's a bunch of BS. So we have subscripts here. Key variables, we have D, T. T stands for time. So the whatever time period, and whenever we just see T without all by itself, we mean the current period. Okay. So D, the subscript T, just means the current period. DT minus 1, that means the period before this one, i.e. the previous period. Just like DT plus 1 would in theory be demand for the next period, but since it's actual demand, we don't know what the demand for the next period is. And if we did, we wouldn't be doing forecasting. We'd be God. N is the number of periods. That's just great because N has been constant through Finance 113, Management Science 103, Management Science 312, and always is some measurement of a count. In this case, it's a count of periods. So, yay, stability. F for the subscript T is the forecast for the current period. So clearly we would have made it in a previous period, but we have our forecast for what we thought the current period would be. We can now compare that to what the actual demand was, see how good we were. Right? So it's still important. And then the all-important forecast for the next period, T plus 1, period after this one. And T plus 2 and T minus 1, and that stuff kind of all goes in your third years. You're smart. You can figure that out. You can count. Use your fingers if you have to. The naive forecast. So first one. We start off with the simple ones, by the way. First prediction, naive forecast. What it will be tomorrow is what it was today. Whoa, deep, man. That's like so cool. All right. So, maybe if in an era of stable demand, where the demand never changes, it just stays the same. There's a certain constant to it. Right? And some staples are somewhat like that. They don't change a whole lot. I normally, if this was a normal period, I'd say toilet paper is that stable thing. But now toilet paper has become, at times, a hot commodity. So I'm struggling. Let's say demand for loose leaf paper, right? It's somewhat stable. Right. Naive method would work. I'm so sad. I lost my good toilet paper example. And so all we just say is that our forecast for the next period is the same as what it was this period. A lot of times we'll use the naive method as sort of an initial estimate. Some of our methods, when we start to get into exponential smoothing models, require us to sort of make some initial good guesses, and often we use the naive forecast as an initial guess. Okay, so not to make fun of it too much. The big problem with the naive model, forecast is susceptible to high or low values. It's fine if demand is very, very stable. Not so fine if the demand or the actual demand fluctuates. Then your naive forecast is going to fluctuate along with it. You can be bouncing all over the place, and all you're really successfully predicting is turmoil. And that's of limited value. Hey, what will things be? Highly variable. Awesome. Great prediction. Or not. Hey, but again, it's easy. It's very simple. It can be a good initial starting point, especially for some of the methods that we'll use later on. But it is susceptible to a lot of variability and volatility. So when we're doing these, estimating these averages, we're going to start off with assuming that there's no overall trend, no seasonal patterns. Cyclical patterns are really hard to deal with in the best case scenario anyway, but we will then relax these restrictions. Okay, so we'll start off no trend, no seasonality, but we'll deal with those in a sec. So stay cool, everybody, stay calm. No need to panic. So, horizontal pattern time series is based on the mean of demands. The forecasted demand is, again, of the future is the average of this time series. So sometimes we'll take, we have the naive model, we just say, hey, the period before is going to be what it is in the period coming up. Or the current period's demand, we expect it to also be the same as the next period's demand. But we can then also do averages for what we think the next period demand will be. Simple moving average, which we've been doing since you were a wee little mathematician in elementary school, and that is just where you sum up some amount of demands and you divide by the amount that you summed up. Okay, you know, pretty basic, right? And it's just we just call that a simple moving average. It's moving because we don't do necessarily an average of all the demands, although we could. We usually pick a subset, you know, 2 or 3 demands, and then just find the averages for those 2 or 3 demands. Oops, whoa, twist, got a little twitchy there. And then the all-important error. We can tell so much from the error. And of course, we all know we want to minimize that error, and that'll be important when we start to use more Excel methods to find, to do modeling when we're finding optimal values of things. We want to minimize that error. What is that error? Error is just simply the demand for a given period minus its forecast for that period, and how much, just how much we are out. Sometimes it's positive, sometimes it's negative, right? And there's a lot of information to whether it's positive or whether it's negative. And we can see that. So for instance, if I think of, okay, well, there's my error. That's just the whatever the demand is minus the forecast. Well, what if that error is positive? What does that mean? Well, that means that when I went to demand minus the forecast, the demand was greater than the forecast, right? No, if that's a consistent, we see that as a consistent pattern, that means the demand is higher than we're forecasting. Our forecasts are undershooting what the actual demand is. Now remember, undershooting, it can be bad too. It means we have not allocated enough resources to making enough product or providing enough service to meet the demand. That represents lost sales. I mean, it's nice that, you know, in theory you say, oh, demand was better than we expected. Yeah, it was, but we planned around a certain forecasted amount, and perhaps we were not necessarily able to meet all that demand, right? We ran out. Maybe people were in a waiting line where they don't like it and they're not happy because people don't like waiting lines and things like that. What if it was a negative error? Right? Well, what does that mean? Well, it means that when I went demand minus forecast, I got a negative number, which means the forecast was higher than the demand. Okay, so maybe we're overshooting. We're thinking demand is higher than it actually turns out to be. And again, we could be misallocating resources as a result. So we actually prefer demand is the same as the forecast, right? Again, we want to minimize those errors. We want to be hitting that demand right on, and because there's a bad side to whether your demand is higher than forecast. There's a bad side to when forecast is higher than demand. Okay, so a lot of information in that error. Doesn't look like much of a formula, right? I mean, 3 letters, a couple of subscripts. Looks pretty simple. Not even an exponent there. but very powerful formula, tells us a lot of information. Okay, let's do some easy peasy examples on this stuff. Bring in our little Excel sheet. So let's talk about that naive method. So here we have some data. This is just made up stuff. So this is nothing too terribly special. We have orders, and in January our actual orders were 120. In February our actual orders were 90. In March our actual orders were 100, and so on, right? All the way down to October, and we're going to assume that November and December haven't happened yet. Okay, so we can then make a prediction. So naive method is we can make a forecast. Whatever's happened in the past will happen in the future. Now we can't make a naive forecast for January because we don't have a previous period's December forecast to work with. But we will forecast that February will be whatever January was. So February forecast. Okay, these are forecasts, not actual numbers. March, well, we'd look at what February was. Well, February was 90. So our forecast for March would have been 90. What's our forecast for April? Well, it's whatever March was, 100. And we go about it and so on, right? Let's do one more. May is whatever the previous period is. It's based off of April. What did we do in April? 75. Okay. So just remember, the forecast for the next period is the same as the forecast for the current period. And that just means that the forecast for May is the demand for April, right? The previous period. Looks like devil, doesn't it? Okay, so now we can think of what's our error in this regard. Well, February, how did we do? Well, we actually had 90. Crap. That was our demand. Minus, we forecast 120. So we had minus 30 as our error. How did we do in March? Okay, we had actual demand in March was 100. Minus the 90. Okay, so 10 to the high side. How did we do in April? Well, actual demand in April was 75. Reading that off the spreadsheet. We forecast 100. And so we have minus 25. How do we do in May? Ooh, May's really bad. 110 was the actual. Forecast was 75. And that's equal to 35 on the high side. Okay, so we have errors. Now, I guess the errors are large-ish in magnitude, but they seem to be positives and negatives. We seem to be overshooting and undershooting. I mean, so there's that. But we can see that we are out by some pretty sizable amounts from one period to the next. Okay, so naive method wasn't really helping us out too much there, but sometimes, like I said before, we use it as a starting point or an initial estimate for maybe more complicated and better forecasting methods. Simple moving average. So a simple moving average, we then now make a we decide how many periods do we want to look at. Okay, so let's look at, let's say, assume that n is equal to 3. So we look at 3 periods. Okay, so when we look at 3 periods, that means the first 3 periods. So let's say D1 plus D2 plus D3 divided by n is equal to 3. That is equal to our forecast for period 4, right? T plus 1. The plus 1 is period 3. 3 plus 1 is 4. I know, when you say that out loud, it sounds like, okay, are you being patronizing, Alan? What's going on here? No, I'm not being patronizing. I'm just trying to keep the subscript straight. Okay, so we can make the forecast for period 4, which in this case is period 1 is January, period 2 is February, period 3 is March, and so period 4, it would be the forecast for April. Okay, so we would look at the January, which is 120, plus 90, plus 100, all divided by 3. Okay. And if my math is correct in my little beanie little brain, we get about 310 over 3, and our forecast to be about 103.3. Okay. So our forecast for April is 103.3. Now we can then look at our forecast for May, and that would be based on February, March, and April, the 3 previous periods. So how did we do in February? We had 90. How did we do in March? We had 100. And how did we do in April? We had 75. And again, we divide those by 3. And so here we're sitting at, what, 265 divided by 3. And that looks to be 88.3. Okay, lots of divide, but thirds, remainder, it's okay. So, but that's the procedure. Now we'll eventually do this on Excel, and it'll be much faster than this sort of slow process. But let's look at error. Okay, let's look at the error for April. Error for April. That's the demand for April minus the forecast for April. And what does that equal to? Well, our demand for April was 75 minus our forecast for April, which was 103.3, right? And that's not looking too good, is it? And so we're looking at about minus 28.3. Okay, so let's flip over to the backside here. Our error, naive method was we were out by 30. The simple moving average we're out by minus 28.3. It's better. Ain't that good, but better. How about the error for May? Error for May, we had the demand for May, which was 110, minus the forecast for May was 88.3. And we can punch that in real quickly, and boom, 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 bang, 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 and out comes 21.7. Okay. How did we do flip side there? Camera zooms in, camera zooms out. Well, we were out by 10 with the naive model. We're now out by 21.7. So, okay, so we've got these estimates. Clearly, there's still some issues. We're still out by some pretty large magnitudes on a period-to-period basis. Okay. So pull that out of there. Now, sometimes what happens is that we're doing simple moving averages, we're doing naive methods, but there could be a pattern in those periods, right? And those patterns in those periods means we want to adjust for that too, right? There's a little bit of randomness, a little volatility period to period, but we want to adjust for that little bit of that volatility. Simple moving average smooths it a teeny tiny bit. The naive model doesn't smooth it at all. And now we can get into weighted moving averages that help smooth it even more. Okay. So now we're going to delve into these smoothing, what we call smoothing models, the weighted moving average and the exponential smoothing average. Okay, both weighted moving averages, both very popular forecasting tools. Okay, so the weighted moving average, yes, if you thought that the subscripts we've seen before looked like, oh my goodness, that looks nasty, those look like something that you're basically your cat puked up on the carpet. And it's essentially the weighted moving average is the way we calculate averages. Simple moving averages assumes that all the weights are the same, and therefore, if the weights are the same, this weighted moving average formula breaks down into, or what they call degenerates into the simple moving average. And we've seen this before. We've seen weighted moving averages in our Finance 113 experience. We've seen weighted type of weighted moving average in Management Science 103 or Stat 151. Expected values are nothing more than a weighted average where those weights are probabilities. Conveniently so, in the weighted moving averages that we'll deal with in Management Science 352, the weights also add up to 1, just like those probability weights added up to 1 in your first stats class. So this is kind of nice that way. Essentially, we look at demands for some number of periods in the past. It could be 1, 2 periods worth of demands, but it could be 3 periods worth of demands, it could be 4 periods worth of demands, whatever. It depends, and we'll see some techniques on how do we optimize that. But so far, it depends, and whatever number of periods we go into the past, there's weights associated with those periods, and we just calculate the average based on those weights. Okay? Now, the formula, I granted, I look at that formula, it looks nasty, man. It takes a pause to kind of try to figure out what is going on there. An example is much faster. Okay. So let's go with the example of Flavorful Pizza. And Flavorful Pizza has recorded the following demand history for each Friday night for the past 5 weeks, and we're going to develop forecasts for week 6. So we want forecast for week 6. This is what we're interested in. For using a 2-period equal weighting for both periods, and a 3-period moving average forecast model, assume the 3-period weights are as stated. Okay. So first case is we're going to assume equal weighting for both periods, and that's essentially the simple moving average. Simple moving average. Equal weights. Okay, so weight 1 is equal to 0.5. Weight 2, 0.5. Okay, that's what we need some data now. Okay, so we look at our data, and there's our demand for the respective period. So when we think of period 3, see, we need we need 2 periods in order to make a forecast. We make a forecast for the period that hasn't happened yet. So we can make the earliest forecast we can make a period for is forecast is for period 3. And so 0.5 times by the week 1 demand, which is 62, plus 0.5 times by the week 2 demand, which is 45. And that gets us our week 3 demand. And we get 53.5. Okay. So there's our warm-up. Okay, a little limbered up now. We don't really care about the forecast for period 3. We care about the forecast for period 6. And so what is that forecast for period 6? Well, 0.5 is the weight. Now, the weight's applied to... Notice how I kept it in time. I did the time period that happens first, then the time period that happens second. We can keep that process, okay? So I'm going to look at first the period that happens first, which is period 4. Okay, so this is demand for 4, plus 0.5 times by the demand for period 5, 60. Okay, that's the demand for period 5. And when I punch that through, I get about 66.5. Okay, so an actual forecast here. And I can do this if I wanted to do a 3-period moving average. All I'm doing is if n is equal to 3, f6 is now just we would if we had equal weighting. Now remember, equal weighting means that weight 1 is a third, weight 2 is a third, weight 3 is a third. Don't just use the half. A half is fine because a half plus a half sums up to 1. Remember, the weights have to sum up to 1. Right? The sum of those weights must equal to 1. It's very important to us. So if they're all equally weighted, we just basically take the number of periods and invert it, essentially, right? If you have 3 periods, that means 1 out of 3 goes into each one. So period 6, now it becomes 1/3. And I keep with the convention of I look at the period that happens first, which is the demand for period 3, which is 55. Right? That's the demand for period 3, plus 1/3 times by the demand for period 4 plus 1/3 times by the demand for period 5. And I get 62.67 is my forecast. So not difficult at all. Not difficult at all. Now, reading along here, we see the question. Assume the 3-period weights are 0.4, 0.35, 0.25, starting with the most recent observation. Okay, so let's look and see what we got here. Starting with the most recent observation would be week 5. Okay, so we think of those weights, 0.8. So let's just write out the weights, and I'll try to skip subscripts too much. So we have the weights. We start off with the weights of 0.4, 0.35, and 0.25. When it says start with the most recent observation, that means that weight 0.4 will be applied to the demand for period 5, the weight for 0.35 would be demand for period 4, and the weight for period 3 would be multiplied by demand for the weight for period 3, which would be 0.25. Okay. So there we could kind of avoid all that nasty looking subscript stuff of the t plus 1 minus I, which gives me a headache every time I look at it as well. So our forecast for period 6 then would be 0.4 times by because that 0.4 is applied to the most recent period, which is demand for period 5, which is 60, plus the 0.35 times by the next most recent demand, times by the 73, plus the 0.25 times by the third most recent demand, 55. Plug that through, 63.3. That's our forecast. So we have quite the variety of forecasts. This forecast very similar to the n is equal to 3 simple moving average forecast. Who's right, who's wrong? Really won't know until we actually get some real period 6 data. Then we'll kind of get a sense. What typically happens, and when we get into doing this on Excel and a little more grunt number crunching, we'll start to see a pattern in the errors, and we'll look at it over a wider period of time to see what we should set those weights are. Is the weighted moving average or some other methodology preferred? Right? So we'll have a little bit more power to that once we start to beef up our Excel skills in this particular area. Okay. So one thing that's really nice about the weighted moving average is that we can emphasize certain demands. Perhaps we understand that the more recent period has a bigger impact or disproportionate impact on what demand will be than, let's say, some demand from 2 or 3 or 4 periods ago. We can make that adjustment by just adjusting the weights. We can also make seasonal adjustments as well. Right? We can adjust it. Okay, we can look at seasonal elements. Maybe we're looking at things 4 months ago. Weight that a certain way, depending on the situation. So we can handle seasonal changes by adjusting the weights. And so the weights give us a lot of flexibility to sort of tweak the model, right? We're taking a simple moving average and we're adjusting it to try to, fit what we see the trends in the data being. Okay. Next unit, we're going to start to delve into the exponential smoothing model. Okay. We'll start the exponential smoothing model by talking about what it is and do a little bit of by hand number crunching, but just like with these other smoothing or these other quantitative methods, Excel will be our go-to for the actual calculations. Okay, thank you.